Hello everyone. Welcome to today's data learning seminar. So today we're very happy to have Youngsoo Choi from the LLNL laboratory. He will talk about interval and structure preserving data-driven methods for physical simulations. Youngsoo, I will leave the audience with you.
All right, thank you so much for the introduction, and thank you for organizing the seminar. Today, I would like to talk about interpretable and structure preserving data-driven methods for physical simulations. These are the collection of methods developed at Lawrence Livermore National Lab, so I will try to combine all of them in a nice story with a consistent theme, that is a interpretability. All right, before I dive into the main presentation, I would like to recognize wonderful student model teams at Lawrence Livermore National Lab, these three people, and plus also wonderful collaborators whom I was fortunate enough to work with, without these collaborators and team members, I wouldn't be able to present what I'm presenting today. So big thanks to all of them. All right, the physical simulations play an important role in modern science. I do not think anyone here will have an objection to what I have just claimed. If the physical simulation were not important, our lab particularly wouldn't have gotten high performance computing facilities on site. Also, if the physical simulations were not important, the concept of digital twins would not have emerged, right? So for example, these days, the various physical simulations have been developed to better understand the process of 3D printing. The simulation for 3D direct energy deposition is one example here, as you can see. And the shockwave, the hydro simulation are important for multiple applications such as automobile, aircraft engineering, or geological science and nuclear physics and so on. And then the electrostatic ion scale turbulence simulation on tokamak fusion device, which is simulated by the production code CoGent, here developed at Lawrence Livermore National Lab, is important for plasma physics point of view. And also the multi-physics simulation such as 3D shape charts is important for national security applications. And the pole collapse simulation you are seeing here is essential to understand the high explosive physics. There are many other important physical simulations, but one potential and major problem with this simulation is their computational cost. Some of them are actually manageable, such as 3D direct energy deposition or 2D shockwave simulations, which takes an hour with multiple cores, are not that bad. However, more involved simulations such as tokamak simulation, 3D shaped chart simulation, and pole collapse simulations are just too expensive computationally. This is unfortunate for many decision-making applications such as design optimization, uncertainty quantification, and inverse problems, because we need to run these four physical simulations many, many times as we explore parameter space. Therefore, we need a fast simulation capability. What if you can do a fancy, complex, multiple physics simulations within a minute with your personal laptop or even with your smartphone? That sounds hard or almost impossible for now, but if it is possible, we can do many cool stuff. For example, you can design things faster that will reduce the cost of the overall manufacturing or analyzing or preparing experimental settings or anything you want to do with physical simulations, right? That would be so awesome. Indeed, today I'm going to talk about how we can accomplish that using data. By the way, let's ponder a little bit about data. data is a cool stuff. If you think about it, it was the observational data that allowed our view change from geocentric to heliocentric world. Collected observational or experimental data were the ones that enable numerous scientific discoveries, such as Newton's law of motion, law of thermodynamics, electromagnetics, and so on. Even now, data plays an important role, especially when machine learning and artificial intelligence are so prevalent. In modern science, the data can do many things, but I will focus on one thing, that is accurately accelerating physical simulations. Because simply being able to accelerate the existing simulations will enable us to do many things we cannot currently do. Well, then how can we accelerate the existing physical simulations with data? Just to illustrate it, let's say we would like to build a fast surrogate model for heterogeneous porous media problems. More specifically, let's say we would like to find out pressure field for a given heterogeneous permeability field. Well, you can first generate simulation data by running many porous media simulations with different heterogeneous permeability inputs. That will give you many pairs of input and output data. Now you can relate these input and output data by, for example, training a neural network. Here we have trained a conditional generative adversarial neural network. Once a neural network is trained, it is easy to predict new pressure field by inserting a new heterogeneous permeability input to the trained neural network. The evaluation of the neural network is fast, and if the quality of the neural network is good, then it will give accurate prediction. For example, the conditional adversarial neural network we trained for this porous media problem, we get accurate solution as demonstrated in these pictures. Full of the model and the surrogate model solutions are basically indistinguishable, as you can see. By the way, this is a black box approach because we blindly relate input and output data with some neural network structure, which we do not have much control on and which we do not understand deeply. So once the neural network is trained with some given data, it is what it is. In that sense, it lacks interpretability and explainability simply because this neural network structure is not familiar enough to us yet. The black box approach is so popular because you only need data. You do not need to know how you solve physics problem numerically. In that sense, it is non-intrusive. You do not need to go inside the physics code and debug things. As long as the simulation data is good, then you are good to go. So it requires less development time than other data-driven approach, which are more involved. Plus, there are great tools out there ready to use, such as PyTorch and TensorFlow and many others. They come with automatic differentiation tools, so you can manipulate the neural network operators very easily to fit into some differential equation forms. However, the black box approach does come with some disadvantage though. Because it relies heavily on data, it needs big data, which is not cheap to generate if the data are coming from computationally expensive simulations. Because it relies heavily on data, the black box model cannot accurately predict the solutions for the regions where you have not seen any data. That is, it is not robust for extrapolations. Plus, the model itself is not easily interpretable, as I mentioned in the previous slide. What if it fails? We do not quite understand why it fails. When it does the job, we do not quite understand why it does the job. Additionally, because the black box approaches do not incorporate any physics information, certain physical properties such as symmetry, positivity, conservation, etc., are not guaranteed to be preserved, which really concerns physicists. Lastly, but not the least importantly, the training of the neural network tends to be very computationally expensive. This point is somewhat arguable because other black box approaches such as Gaussian process or Kriging or random forest are easy to train. I'm specifically addressing this issue with neural networks. Its training is computationally expensive because it involves complex nonlinear optimization solves. Plus, it converges behavior. It's a convergence behavior can be very problematic. Well, then how can we get an interpretability? We have to somehow relate this data-driven model with what we are familiar with already, the things we have studied for a long time. For example, ordinary differential equations or partial differential equations. To illustrate that, let me consider a simple radial advection problem, which is described by a well-known partial differential equation. You solve it using some numerical schemes, such as finite element or finite difference methods, then generate simulation data. This data is high dimensional, so it would be hard to fit them directly into some model. Plus, remember that our goal is to build a fast model. To build a fast surrogate model, we better deal with a reduced space dimensions. So we compress the data, which, for example, leads to the latent space dynamics data with dimension of only 3. There are two types of compression in general. First one is linear compression. Proper orthogonal decomposition, tensor decomposition fall into this category. And the other one is nonlinear compression, autoencoder, generative adversarial network, and so on, falls into the nonlinear compression category. Now going back to the latent space dynamics data, this low dimensional data is a lot easier and more manageable to fit into a model. Which model would you use? Note that it is time-dependent data. Remember, Isaac Newton wanted to describe orbital motions, which is also time-dependent data with a model. What did he come up with in the process? The calculus or differential equations. Yes, we can fit the latent space data into differential equations. For example, linear ordinary differential equations or quadratic differential equations, and so on. By the way, if we choose to use linear differential equation, then we are more or less using the famous method that is dynamic mode decomposition, so-called DMD. The DMD fits latent space dynamics into linear ODE model. We know a lot more about linear ODE than a neural network. So this approach is, although purely data-driven, it is interpretable. For example, if we happen to know this A hat matrix here, explicitly, we can perform eigenvalue decomposition and write an analytical solution for the linear ODE in terms of eigenvectors and eigenvalues. For example, if the real part of the eigenvalue is greater than 1, then the solution will explode. Therefore, we should make sure that eigenvalues does not exceed 1 if we know that the true solution does not explode. Here, eigenvalue serves as an indicator, which tells us why the model fails, if it fails, and so on. By the way, the DMD that requires only data, so it is not an intrusive method, which requires less development times than other intrusive methods. So we were able to apply this DMD to many different physics problems pretty quickly. Let me introduce some of them now. The first DMD example is on the heat conduction problems. DMD can be parameterized easily by interpolating DMD operators. To demonstrate the parametric capability, we set 3 parameters, that is the radius of the circular initial condition and the x and y coordinates of the center of the circle. By following the same the procedure of generating training data and the building DMD, it has been tested for several points which were not used in the training sets. As you can see, the DMD was able to predict the solution quite accurately, less than or close to relative error of less than 1% error. All right. Another engineering problem that we have applied DMD to was 3D printing process. Not long ago, 3D printing has revolutionized the manufacturing sector. With 3D printing, you can make almost any object with any complex shape. In order to make a 3D printing process as precise as possible, it is important to be able to accurately simulate the 3D printing process. As the 3D printing simulation model becomes complex, though, the computational cost becomes too much. For example, the full order model of this simple laser hitting the testbed process simulation takes a couple of days, while the DMD simulations here and here takes a couple of minutes, achieving a great speed up. Plus, a great accuracy was achieved. That is a relative error around 2%. Another physics problem that we have applied DMD to was pore collapse simulations. By the way, this is very interesting physics. When shock wave hits the pore in the middle, it is hard to see the pore in the middle because we are visualizing temperature field, but right here, that was where the pore was. It introduces interesting hotspots. The pore collapse simulation is notoriously known to be very computationally expensive. This particular full order model simulation takes a day. However, DMD was very fast, taking 1 minute for training and 8.3 seconds for DMD evaluations. By the way, this speed up was achieved without losing much accuracy at all. The DMD achieves a relative error around 0.2%, which is basically indistinguishable with the full order model solution. Another nice thing about DMD is that the training cost is not comparable to the one for neural network. For example, we have applied both neural network black box approach and DMD to shock-induced the flyer plate dynamics problem, where generating a full order model takes 52 minutes. Neural network training time was 4 hours, while the training of DMD took only 4 minutes. Interesting fact is that this neural network used downscaled data. That is, the original full order model data was actually 2048 by 1349, but the downscaled data for neural network was 128 by 128. Despite this, the reduced size of data, neural network took 4 hours of training. On the other hand, the DMD did not need to downscale the data with the original size data. DMD was able to train it within 5 minutes. Well, also look at the accuracy. The DMD gave a better accuracy than the neural network. I would say that this shows a power of interpretable DMD. We have also applied the DMD to Kelvin-Helmholtz's instability problem, where we achieved 900 speed up with a relative error of 1%, which again is a wonderful result. Finally, DMD has been successfully applied to other interesting physics, such as 1D, 1B Vlasov plasma physics problem for two-stream instability, 2D Euler equation for Riemann problem, and 2D Navier-Stokes equation for lead-driven cavity problem. For all of these problems, DMD was able to generate not only good accuracy solutions, but also considerable speed up, such as 33.4, 79.3, and around 2000. All right, enough for the DMD stuff. Now I would like to ask the following questions. Are there data-driven methods other than DMD which are interpretable? The answer is, of course, yes. Let's go back to the radial advection problem for DMD. After the compression of the high-dimensional simulation data to a lower dimensional latent space, we fit the reduced dimensional data to linear ODE. However, it may be the linear ODE. It may be that the linear ODE is not a good choice. Actually, one can imagine fitting the latent space dynamics data to higher order ODEs, or even to an ODE with trigonometric or exponential right-hand side. This is exactly what the LaSDI does, which stands for latent space dynamics identification method. SIMD type of the sparse regression technique can be used to fit the latent space data to user-defined ODE. But we do not enforce sparsity when we do the regression, because our main motivation is not to come up with an ODE with sparse terms, but to best fit the data to given ODEs by minimizing the error. This approach is again interpretable because our latent space dynamics model has a familiar ODE form. Now we want to make this LaSDI framework robustly accurate when the parameter changes. There are many different ways of making the framework parametric. First of all, we only want to deal with the latent space model, not the full order model, which implies that parameterization must be done within the latent space. Let me show you one way of doing it. Here is a parameter space D for each training parameter point. For example, parameter point mu1, we can build a tailored ODE that best describes the latent space dynamics at that point. Note that coefficient matrix A hat depends explicitly on mu sub 1. You can do the same thing for mu2, mu3, and mu4 and mu5 and so on. Then you can interpolate the linear coefficient of the ODE for the testing point mu star. Note that the coefficient, the matrix A, depends explicitly on the testing parameter mu star, as well as all the training points. As you can see, you can apply a similar interpolation for other testing points as well. We have applied this LaSDI framework to the radial advection problem by parameterizing initial condition with two frequency values, W1 and W2. For this particular problem, we took uniformly sampled training points as shown in this graph, 5 by 5, which give 25 training points in total. For each training point, we generated the high dimensional simulation data, then we compressed them to latent space dynamics dimension of 3 using the autoencoder. Then the coefficient of ODEs that fits the latent space dynamics data were interpolated. This heat map shows the relative error on a given parameter space. The maximum relative error was 5.4% that occurred along this line. The LaSDI framework was able to give us a speed up of 200 when compared to the full auto model simulations. Decent results, right? But we were not happy about the high relative error concentrated on the particular region of the parameter space. For this particular problem, it seems to happen on the right side of the parameter space right here. This was caused by the uniform sampling. We needed a better sampling procedure, possibly by incorporating physics information. We have actually developed such a non-uniform sampling procedure that is guided by the underlying physics. When we applied it to the same radial advection problem, we got better accuracy, even though we used the same number of the training points, that is 25 training points in total. The heat map on the right shows relative error distribution on the parameter space when the physics-informed greedy sampling is used. As you can see, the training points were not sampled uniformly. More samples were chosen on the right bottom corners, which makes sense because the relative error with the uniform sampling were high on those right bottom corners. With this physics-guided non-uniform sampling, we were able to achieve a maximum relative error of 2%. This time, the maximum relative error happens on the left side of the parameter space, which makes sense. So how do we do it? We followed an active learning paradigm where you adaptively append training data while the autoencoder is being trained. For example, you start with the 4 corner points in the parameter space, which were marked by 4 empty squares where we run simulation data. Then we check if the number of training points reach the maximum allowed. Let's say we are willing to spend 10 training points in total. Since we only have 4, we are going to move on to the training of autoencoder and the dynamics identification process. Because the autoencoder and the dynamics identification steps must communicate with this adaptive sampling procedure, we combine the latent dynamics identification steps into the autoencoder training by adding the latent space dynamics regression terms as loss functions terms. So there are 3 terms in total in the loss function. The first one is a typical reconstruction loss for autoencoder, which takes the difference between original high-dimensional simulation data with the reconstructed one through the encoder and decoder. The second and the third loss terms are related to the latent space dynamics regression terms. We go through several epochs to pass, say, for example, the 2000 epochs to minimize these loss terms simultaneously with the current training data. Then we go back to sampling where we apply random validation points. At each validation point, we compute the physics-informed error indicator. We find out where the maximum physics error indicator occurs with the current autoencoder and the dynamics identification model. In this picture, these red points gave us the maximum error. So we take it as a training data and generate a simulation data there and add it to the autoencoder training. And we repeat this process until the desired accuracy or the maximum number of training points are reached. If you want to know more details about this physics-informed greedy sampling procedure, you can check out this paper, or I have a short YouTube video that explains it. You're welcome to check this out. It's less than 10 minutes, so I'm sure you will enjoy it. All right, enough for interpretable data-driven methods for now. How about physics-constrained data-driven approach in order to perhaps to preserve some structure, underlying structure by underlying physics? If you can somehow incorporate the physics in your data-driven methods, it will be for sure interpretable. And that would be the most desirable things, because it will be easier now to preserve some underlying structures such as conservation, symmetry, and positivity. To discuss that, let's go back to the page where I described the process of compressing high-dimensional data. Again, after the compression, you get the latent space dynamics data with a reduced dimension. As usual, the interpretable data-driven approach was to fit these data into a user-defined ODE, ordinary differential equations. Well, instead, what if you derive a system of ODEs that describes the latent space dynamics data from the original governing equation? Is it even possible? The answer is yes. One way of building such a system of ODEs for the latent space dynamics is given by traditional projection-based reduced order model. To explain it, let's start with these governing equations represented by the ordinary differential equations. You can consider it as a semi-discretized version of the partial differential equations that describe your underlying physics. Here, W is a state variable, F is a nonlinear function, and T is the time variable, and mu is a parameter. We first approximate the solution as a linear combination of reduced basis phi, whose dimension is a lot smaller than the full order model dimension, big and so vast. Then you plug this solution representation into the governing equations, you will end up with an overdetermined system where you have more equations than the unknowns. So to close the system, you apply some kind of projection. Here I have applied the Galerkin projection that gives a reduced system of ordinary differential equations. By the way, this ordinary differential equation describes the latent space dynamics, which was completely derived from the original governing equation that describes the underlying physics. So this is a physics constraint or physics informed latent space dynamics discovery approach. Then you can apply your favorite time integrator to this reduced system. For example, the backward Euler time integrator has been applied here just for the demonstration purpose. This gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. The history of the projection-based reduced model development is very rich. It has been successfully applied to many different applications. For example, we were able to extend the traditional projection-based reduced model to time windowing approach and apply it to several Lagrangian hydrodynamics problems. Here you are looking at the cases where the reduced order model achieves a speedup of 14.6 to 87.8 with an indistinguishable accuracy level, and that is a relative error less than 0.1%. There are many variations of the projection-based reduced order models. For example, the solution does not always have to be represented by a linear combination of reduced spaces. It can be completely nonlinear, as it is depicted in this slide. The decoder neural network can be used as a solution representation. If you do that, then you will get a superior performance to linear subspace approach. For example, here we compare the performance of different types of survey models that I have introduced in this presentation. The full order model is FOM, and then ROM is a nonlinear manifold reduced order model. LS-ROM is linear subspace reduced order model, and deep fluid is a type of black box approach. As you can see from the movies, NM-ROM and the full order model are almost identical in eyeball norms, although NM-ROM used a latent space dimension of only 5. Quantitatively, NM-ROM achieves less than 1% maximum relative error. Furthermore, a speedup of 11 is achieved by the NM-ROM, while LS-ROM and deep fluids are struggling to achieve a precise solution. Another interesting variant of the projection-based reduced order model is, I'm sorry for the movie, but this full order model, the movie is almost identical to the reduced order model movie. But this demonstrates the space-time reduced order model, where not only the spatial domain complexity is reduced, but also the temporal domain complexity is reduced as well. Using the space-time reduced order models, we were able to reduce the 10 billion degrees of freedom to only 10, and still gets the pretty much the same physics response as shown in the movie. The full order model took 17.4 seconds with the 256 cores, which is not bad, but the space-time reduced model was able to finish the simulation within 0.006 seconds with only 1 core. That gives us a wall time speedup of around 2,700. Quantitatively, the relative error was less than 10% throughout the time history. Okay, the physics constrained projection-based reduced model have also been successfully applied to accelerate design optimization process. For example, let's see. Hopefully the movie is playing. Okay, for example, here is a numerical demonstration for latent lattice structure designed using component-wise reduced order model. Here we minimize the compliance, imposing a constraint of the mass being at most 40%. The downward pressure force is applied on the top, and on the bottom, there's the Dirichlet boundary condition is applied. The full order model monolithic finite element solves involves 2.7 million degrees of freedom for this particular problem, while the component reduced order model has only around 4,000 degrees of freedom. The movie, which unfortunately is not playing somehow. I'm not sure why. Oh, okay. Yeah, this movie demonstrates the process of the optimization history. Initially, it started with a uniform density. Initially, it started with the the uniform density variable, and it evolves to the optimal design, where the blue component implies no material there, while the red component implies that you put the materials there. With the component-wise reduced model, a speedup of 660 was achieved, and a tunable accuracy for a relative error less than 1% down to 10 to the negative 8 was also achieved. All right, the component-wise reduced model lattice structure, the design can be applied for a stress constraint problem, where the mass is minimized and with some stress constraints. That is considered a harder problem than minimizing the compliance problem. Here we achieve a speedup of around 150 times with the component-wise reduced model with less than 5% relative error in stress measure. This is quite an achievement because it is usually hard to obtain an accurate stress measure with a surrogate models for lattice structures, such as homogenization-based method or the beam or truss-like structures. As you can see from this zoomed picture, component-wise reduced model is able to bring high fidelity accuracy for stress quantity everywhere in the computational domain. The projection-based reduced models can be also used as a preconditioner for the linear system of equation solves that occurs during the design optimization problems. Here we have applied the reduced model preconditioner for the wind turbine blade design problem, and the reduced model was able to achieve a speedup of 3.5 times, and it converges to the same optimal 3D blade optimal design. Another type of projection-based reduced model that is a data-driven, data-based local reduced model can accelerate this time multi-start airplane wing optimization process. Multi-start strategy is commonly used to solve robust optimization problem. It needs to solve many optimization problems with different starting points. In this setting, once for all trained local reduced models were reused to ultimately achieve a speedup of 32.4. Okay, all right, so much for the physics constraint projection-based reduced models. Let me conclude the talk with some summary. The data-driven methods for physical simulation can be categorized by its level of intrusiveness. For example, black box approach, denoted as BB, is the least intrusive method requiring only data, as I mentioned in the beginning of the talk. Then we can think of more interpretable methods which also use only data, but then try to come up with a model that is more understandable or interpretable than the neural network type black box approaches. Then the most intrusive methods, that is the physics constraint methods, can be the last category. Roughly speaking, more intrusiveness means more accuracy. So the intrusive physics constraints, the reduced order models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the black box methods is faster than the intrusive reduced order models in general. Also, the physics, the constraint reduced order models are more robust in extrapolation than the black box reduced order models, which become very handy when solving a PDE constraint optimization, such as design optimization. If you are interested in generating the numerical results that I have shown you today, you can use our open source software tools for data-driven physical simulations, that is Libram, which you can find it from the GitHub page. Also, useful documents and examples are given in the Libram webpage. That is libram.net here. So please take advantage of it. With that, let me conclude my talk, and thank you for your attention, and any questions are welcome.
Thank you, Youngsoo, for the nice talk. It was very impressive. So for the audience, if you have any questions, you can either raise your hands, or if you don't want to show yourself in this video. So we're actually recording. In that case, you can also type your question in the comment box and I will read that for you. So I saw already a hand. So Fred, if you would like to unmute yourself and ask a question.
Sorry, Cedar, that was actually a clap. I haven't got a question, but I'll try and think of one. So maybe move on to someone else if they do have a question right now. Sorry about that.
Okay. Yeah. So anyone else, if you have a question, please do not hesitate to raise your hands. So at the same time, actually, I have a couple of questions, so maybe I can start with. So Youngsoon, I don't remember the exact number of slides, but at some point when you present the physics-based greedy sampling methods, so we can see that you can transform the arrow distribution. So I think where you present the heat map, at the beginning, you can see a high value of the arrows on the board, and then yeah, exactly this one. And then you transform that to like on the left side, as you said. So I was wondering if you continue this iterative process, for example, if I understand well, that will continue to reduce the arrow that presented on heat map, but will we have any control in terms of the distribution of this arrow? What I mean is, if we continue this process, well, the change of this heat map being quite stochastic, sometimes from the left to the right, and reverse of that, or it will get some point and to be quite stable, like keep the current form.
It's guaranteed to reduce the maximum error in your parameter space as you add more points. So, I mean, you know, you're right, and it's going to the maximum error can move from left side to the right side, or top to bottom, or bottom to top. However, the absolute value of the maximum error will decrease monotonically as you add more points. So, for example, right now the maximum error is 2% around the left-hand side. So this is the maximum error points. So what we are going to do is we are going to add the data at this point, right? And then it's guaranteed that around these regions, the error will be decreasing. And, you know, probably some other points like the 1.5 here and there will be the next, the maximum error points. And you add those 2 points, then, you know, as you can see, the accuracy improves monotonically as we include more points, data points. Yeah.
Okay. Yeah. Thanks, Youngsoon. And yeah, actually, I have another question. Is when you present the second part, the physics-informed reduced order modeling. So it seems that you have problems with adaptive mesh that you present. So I was wondering, here you present the methods mainly based on the linear-based projection, reduced order modeling. Have you considered to use like neural network-based methods for adaptive mesh? And also with the physics constraints as well.
Well, this slide is well, I have went through this slide pretty quickly, but you know, initially, yes, you're right that we represent the solution as a linear combination, so we use the linear subspace. However, here we replace those solution representation with a nonlinear manifold, which is represented by a decoder of the autoencoder, which is designed by the neural network. And we plug this nonlinear manifold form into going back to the governing equations. And so this is physics constrained.
Okay. So the additional form actually is from the neural network reconstruction, right?
Yeah, exactly. And, you know, as you know, the neural network is, you know, has a lot more expressibility than the linear subspace. So it does, even though this is advection dominated problems, the nonlinear manifold with this model, which uses the neural network, the nonlinear manifold, the solution representation is doing much better than the linear subspace solution, where the fictitious, you know, front is showing, and even the black box approach, you know, exhibits some high relative error, which is 38.6% for scientific applications. This is not good enough. So yeah, definitely introducing neural network in your physics constraint data-driven method is definitely helpful.
Yeah, thanks for explaining that. So I think we have some questions from the audience in the chat. So first is from Cedric. So he said maybe a comment on uncertainty quantification in case of extrapolation. So in particular for physics constraint cases, supposed to be more robust in case of extrapolation.
Yeah, exactly. Because I mean, okay, if you think about it, if you are familiar with the usual numerical schemes like the finite element or finite volumes, what you're using is a for example, finite elements. Each element you represent the solutions with some polynomial, a set of the polynomials, predefined basis. And even though you're using the predefined basis, as you refine the mesh, it is guaranteed that by convergence theory, it will converge to the true solutions of whatever the solution of the PDE you're dealing with. There is everything is extrapolations because we have not used any data. We have used only the governing equations, which describes the governing equation, the physics. So that's purely data driven, and as you but that logic goes along against when we apply the data driven approach. When we apply the data-driven approach, as we add more physics information to the approach, the extrapolations capability will be improved because we are using the physics to guide the extrapolations. But if you are not using physics, if you use only the data, then the model you construct will be only accurate where the data is seen or the insight, which is interpolation regions, not the extrapolation regions. So yes, definitely, if you use the physics constraint method, then you will get the better extrapolation capability. For example, I mean, I have not shown the results, but I have the results for these problems for the extrapolations. Although this reduced model was produced for a particular point in the parameter space, going away from that, the accuracy of the reduced model was not that degenerated. I still maintained the relative error less than 1% in the extrapolation reason because the physics was the informed and the constraint.
Yeah, thanks, Youngsoo, for the answer, and hope that's good for you, Cedric, and thank you for your question. So we have another question from Praka, and what he said is in the same sampling slide. I think he meant the greedy sampling slides. Don't know if physics informed greedy sampling would work for unstructured data.
Unstructured data. I'm not sure what you mean by unstructured data, actually. I mean, it's not the uniformly graded the data. If that's what you mean, yes. I mean, there's no reason that it shouldn't work for the unstructured data, as long as we can get the residual information from the PDE. Actually, this is the, some of them is using the unstructured data, unstructured mesh, or even the mesh is moving with the time goes on, because it's a Lagrangian the formulation. It uses the Lagrangian formulation. As you can see, the mesh is moving with the field. As long as we can get the residual informations, which carry some physics informations, yeah, it is applicable for the unstructured data as well.
Yeah, thank you, Youngsoo. And Prakra just would like to thank you for your answer. So for the audience, if you have any other questions, please do not hesitate either to leave your questions in the comments, or you can unmute yourself.
Someone tries to talk, but
Oh, yeah, I see David has unmuted yourself. So David, do you have a question? Or if you have problem of your microphone, maybe you can leave your question in the comments and I will read it out for you. Okay, and if not, I think Dr. Cho will be very happy if you would like to ask him questions by sending an email after the presentation.
Definitely, yeah. Anyone can send me an email. My email address is right here. Yeah, you're welcome to send me an email with any questions. I'll be happy to answer.
If we don't have any other questions for now, I would like just to thank again for Dr. Cho to join us today and for accepting our invitation to give this very clear and very impressive talk. Thanks again. And thank you everyone for joining us. So hopefully to see you for the next seminar of data learning talk. Thank you. And so have a nice evening for everyone in Europe and have a nice day to Youngsoo. Thank you again for giving this talk.
Thank you. Thank you, Sibo. Nice to meeting you.
Thank you. Bye.
Thank you.